Great. So this is chapter 6, and we are going to talk about what are called discrete probability distributions. In the first section here, we're going to, again, go between review what discrete and continuous variables are. This is a concept we discussed very, very early on in our class. We are then going to look at discrete probability distributions. We are going to graph them, and then we can compute and interpret the mean of a discrete random variable and discuss that is also called the expected value. Kind of a continuation of some probability stuff that we just finished up. First, how do we distinguish between discrete and continuous random variables? A random variable is a numerical measure of the outcome of a probability experiment. So its value is determined by chance. Random variables are denoted using the letter like capital X. The discrete random variable has either a finite or countable number of values. The values of a discrete random variable can be plotted on a number line, and there's going to be space between each point. So if I have that number line, it's going to show me here, I've got 0 exactly, 1 exactly, 2 exactly, 3 exactly, 4 exactly. Okay, if it is a continuous random variable, that means we have infinitely many values. And what that means is I can take on any value in between a start and a finish. So any value between 0 and 1. I mean, 0.01, 0.000256. I mean, it can be any number in between there. All right, so the first thing we are going to do is decide, do we have a discrete? Do we have continuous? Number of A's earned in a section of statistics with 15 students enrolled is a discrete random variable because its value results from counting. If the random variable X represents the number of A's, then the possible values of X are 0, 1, all the way up to 15. We have 15 total students, and if I'm counting the number of A's, keyword there is I'm counting A's. You either got an A or you didn't. There is no in between, so it's either a whole number or not. Similarly, the number of cars that travel through a McDonald's drive-through in the next hour is a discrete random variable because its value results from counting. Again, I'm going to count the number of cars. It is a whole value. You're either a car or not. There is no in between here. The speed of the next car that passes a state trooper is a continuous random variable because speed is measured. So, biggest difference here is if it is counted, it is discrete. If it is something you are measuring, it is continuous. And a lot of you use those words when filling out those lecture questions of how you describe the difference between discrete and continuous. It was one of the first lecture questions you had to answer. Okay, so counted or measured. Anything that you measure is going to be able to be determined to different levels of accuracy. Maybe I'm traveling 45.6 miles per hour. If they have a speed gun, they're going to get decimal points and it's a measured value. So it is continuous. Looking at our probability distributions that we had in chapter 5, we'll be able to determine some of those were in fact what are called probability distributions. Okay. The probability distribution of a discrete random variable X provides the possible values of the random variable and their corresponding probabilities. A probability distribution can be in the form of a table, a graph, or a mathematical formula. We looked at some of these in chapter 5 without knowing that this is what you were looking at in table form. Suppose we ask a basketball player to shoot 3 free throws. Let the random variable X represent the number of shots made. So he either makes 0 shots, 1 shot, 2 shots, or all 3 shots. And then we repeat this process over and over and over again to figure out how many times he gets none, how many times he gets 1, how many times he gets 2, how many times he gets 3. And then you divide that to figure out the probabilities. So he gets 0, 1% of the time, 1, 10% of the time, 2, 38% of the time, and all 3, 51% of the time. So we had tables like this. This was our relative frequency. This is what we calculated in a relative frequency table. So this should not be new to you. We can denote any probability P of X. You know that from chapter 5, where X then is the specific value that we want to know. So we read P of X as the probability that the random variable X equals X. For example, P of 3 is asking what's the probability that you get 3 free throws? And the probability of getting 3 free throws is 0.51. So in order for us to have a discrete probability distribution, if I add all of the probabilities together, I should sum to exactly 1. And every single probability should be between 0 and 1 inclusive. So, hey, when I asked you in chapter 5, is this a probability distribution? You checked for these two things. You added all the probabilities together, and if they sum to 1, you said, yes, it's probability distribution, as long as every single one of those was between 0 and 1. Same is going to work here. Exactly what we worked with in the tables. Is this first one here a probability distribution? So I immediately, before I even sum these up here, I see that this is a negative down here. So no, sorry, can't do it. Not a probability distribution because I have a negative. Probability cannot be negative. So this is not a discrete probability because the probability of 5 is a negative value. Less than 0 cannot happen. Next one. All right, is it a probability distribution? So all of them are positive. I'm going to start adding. If this is 49, okay, so 49, 20, if I add these, 20, 45, 55, that's way over 1. Because 55 and 49 is over 1. So if I sum them all up, I get 1.18, not a probability distribution. Again, that is something that you were able to pick out in chapter 5. We'll look at C. Again, all of them are positive. So I will just go ahead and show you the sum here. This one does sum to 1 exactly. You could double check it if you want to. But 20, 45, 55, 65, 69, 70, add 30 more to that is 100 exactly. So 1.00. You got it. How do we graph them though? What is that going to look like? We want to graph. This probability here was the free throw probability that we first worked with. The way this is going to work, you are going to create a probability graph. It's going to have your relative frequency probability here and all of your values along the horizontal axis here. You're going to see that each of these are distinct. Okay? This is called a discrete probability histogram. And when you think of a histogram, normally you think these two bars would touch. But because this is discrete, and there is no way for these two values to overlap, for a discrete probability distribution, what's going to happen is you're going to put a dot where that probability occurs, and then just draw a vertical line. So 0.1, vertical line. 0.38, vertical line. 0.51, vertical line. Okay. StatCrunch does do this for us, and I will show you how to do that. Free throws and probability. 0, 1, 2, and 3. 0.01, 0.10, 0.38, and 0.51. There it is. Under stats. Okay, stats, calculators, custom. So our values are our free throws. Weight is another term for probability. So that is going to be this guy here. And I'm going to click compute. And it is going to make my graph right here. if you compare, it should look the same. So now let's calculate the mean of our random variable. The mean of our discrete random variable is found by the formula. Mu sub x is the sum of all of the x's times the probability of those x's. So x is the value of the variable and p of x is the probability of getting that value. And just so you know, StatCrunch did show that to us. It does calculate the mean and standard deviation for us. So I'm going to show you how we can double check that it is correct. Okay, so we're going to use the table, that same table that we had. This was the table. So your first step is to multiply across here. So 0 times 0.01 is 0. 1 times 0.10, 0.1. 2 times 0.38 is 0.76. 3 times 0.51 is 1.53. And then the last thing you're going to do is sum all of those together, and that's going to give you your mean. Add all of them together, and you get roughly 2.39. If I wanted to round to one decimal place, it would be 2.4. And let's verify. 2.39 is exactly what StatCrunch gave us. So you have your choice. You can calculate it out with a calculator, or you can use StatCrunch to help you do that. So what does it mean though? So after we compute it, what does it mean? Mean, not to be confused with what does it mean. Mean of a random variable represents what we would expect to happen in the long run. It's also called the expected value. So for the problem we just looked at, this is the number of free throws. If we go back to this particular basketball player, we would expect him to get around 2 free throws every time if he had to do 3 back-to-back. We're a little closer to 2, so somewhere between 2 and 3, but a little closer to 2. All right, so E of x is what we call the expected value. E of x, or the expected value, is the same as the mean of the probability distribution. So what you can do is you can use this for, I think, insurance, sorry. Lots of insurance people they determine how much of a risk you are, and then we'll give you rates and different things based on your risk. If you are a higher risk, you're going to have to put more money into it versus if you're a lower risk, you don't have to put in as much, and then they can kind of figure out overall for all these kind of people, what's the expected value kind of deal. Long-term life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. Suppose an 18-year-old male buys a $250,000 one-year term life insurance policy for $350. According to the National Vital Statistics Report, Volume 58, number 21, the probability that that male, age 18, will survive the year is 0.998937. Compute the expected value of this policy to the insurance company. Okay, you're 18 years old. You're not going to be likely to pass away in the next year. So they're very easily going to give you a larger insurance payout for a minimal fee. Okay, what's the expected value for the insurance company? If they survive, so here we got 2 things. We've got here we survive or we die. Those are our 2 choices. The insurance company will gain $350 if the 18-year-old survives. And they told us that that probability was 0.998937. Which means that if the 18-year-old dies, they would have to put out that $250,000 minus that $350, right? They would have gotten that $350, but they would have to pay out $250,000. So that is a difference of $249,650, and that is negative money to the insurance company. Okay, that was money they would pay out. Lastly, we have to figure out the probability of this happening. Well, if we have the probability you survive, the probability you die is your complement, or 1 minus 0.998937, and that gives you 0.001063. The first thing is taking that information from the problem and creating our probability table. It can get a little confusing, but if we do a few more, hopefully it'll make a little more sense. All right, so then we have to find the expected value. So what we're going to do is just multiply here, 350 times its probability, negative 249,650 times its probability, and add the two values together. And based on this, if they were to work with all 18-year-olds, their overall expected value for 18-year-olds is to make $84.25. So they're going to offer those policies to those 18-year-olds because they're going to bank money in the end. And a 1-year policy, if you pay that $350 and you don't die, the $350 is gone. Your benefits are done because you had a 1-year term. So like I said, the company expects to make $84.25 for each 18-year-old male client that it would insure. The $84.25 profit of the insurance company is a long-term result. It is not going to make that amount on every individual, okay? It's what happens when you take all of your 18-year-olds and combine them together. This is how companies determine if they want to take a risk with you. Are you going to be someone that in average and long term is going to make that money, or are you going to be someone that makes them lose money? Okay. All right, that is the end of that section. But before we move on, I'm going to pull up a few of the homework questions just so we can practice. Okay, so this is just, is it discrete? Is it a probability distribution? Is it a probability distribution? Those are pretty straightforward. This one here is saying determine the required value of the missing probability to make it a discrete probability distribution. All right, so taking a look at this, if I have 3 of the 4 values and I know what the sum is, then I can add these up and subtract from 1 to find what's left. Okay, we've got a probability graph, and it's going to ask you different questions based on the graph, and also has little numbers above here. So what's the probability that a randomly selected 51 to 56-year-old mother who had a live birth in 2015 is her 4th live birth? So 4th would be 0.109. So you're just looking at the graph, reading some values off of the graph. Pretty straightforward. Yes, I want to leave the question. Okay, so here's one expected value one. So investment counselor calls with a hot stock tip. He believes that if the economy remains strong, the investment will result in a profit of $50,000. If the economy grows at a moderate pace, the investment will profit $10,000. However, if the economy goes into recession, the investment will result in a loss of $50,000. You contact the economist who believes there's a 20% probability the economy will remain strong, 70% probability the economy will grow at a moderate pace, and a 10% probability the economy will slip into a recession. What's the expected profit? So what I'm going to do is I'm going to put this over here and go back here and get my StatCrunch. And I'm just going to enter it in StatCrunch so you can see all the values here. Okay, so we can make a profit of 50,000, 10,000, or negative 50,000. The probability of the first one is 20. The probability of the second one is 70, and the probability of the last one is 10. To find the expected value, it's under stats, calculators, and custom down here. Our values are the first variable, our weights are the second variable. I'm going to click compute, and the mean here is the expected value. So 12,000 is my expected value. Ta-da! Pretty straightforward, but you have to create the table first. All right. So another one, verify, and then calculate. And then that goes into the next section. So yeah, hopefully that helps a little bit with the homework questions. Pretty straightforward as far as you can use StatCrunch here. That is the end of section 6.1, and I will see you in section 6.2.